The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, good morning, good evening, good night, everybody, wherever you are from different parts of the world. My name is Krishna Vedula, and I'm coordinating this IFEAS webinar series. This is our webinar speaker is Dr. Khairia Muhammad Yusuf. He's a professor and director for Center of Engineering Education, University of Technology, Malaysia, president of the Society of Engineering Education, Malaysia. And as you can see, the topic is there, and I'm sure you're all waiting eagerly for her to get started. So if at any time during the presentation, please feel free to send text messages so that I can keep track of them and we can address them once in a way. Okay. So it's over to you, Dr. Khairia.
Okay, thank you, Professor Krishna Vedula. Bismillahirrahmanirrahim, Assalamualaikum, and greetings everyone. Thank you for tuning into the webinar. I hope you will have a productive hour here. I will introduce to you what is cooperative problem-based learning and how it can be used in a typical classroom. And also, we can have discussions on how it can be used in your own classroom. So if you know that we are now currently facing, there's a lot of talk about Industry 4.0, how things are getting more and more complex and everything is changing very fast, especially with technology and the computing power getting very high. So I'm not going to dwell too much into this, but this is all the backdrop of why all of a sudden, you see the requirement for complex problem solving popping up everywhere. This is the latest report from the World Economic Forum 2018, where they put out the 2022 skills outlook. And of course, again, complex problem solving is one of the skills. But if you really scrutinize the 10 growing skills, those are all actually components of complex problem solving. So it's clear that wherever we are, we need to be able to adapt and actually equip our students on how to deal with complex problems because of what is happening in the world today. Now, the 2015 New Vision for Education report actually defines what are 21st century skills. And if you can see, we are normally focusing on the foundational literacies. No doubt that is very, very important, but there's also the competencies and the character qualities. Now, if we try to just focus in on one skill using one technique, it can be very overwhelming. So is there a way where we can teach our students with one approach where we have an approach that is powerful enough and flexible enough to allow us to pick the kind of skills that's needed easily? Now, if you look at the Washington Accord program outcomes, you see the word complex engineering problems, complex engineering activities popping out again everywhere. So that's just half of it. If you look at the other half, there's also more. And so is the question that we have now is, how do we develop the required 21st century skills, especially the skill like complex problem solving and also deep learning in a typical classroom? Because no doubt there are ways to develop this, but sometimes the cost is quite high. So how can we do it at least as a start in our own typical classroom setting? Now, if you look at this active learning continuum, there's various ways with a whole range of techniques ranging from just making the class active, which is more instructor-centered, to on the other side that is really more highly student-centered, like problem-based learning. Well, in between, of course, there are variations. The thing is, although problem-based learning can be very powerful, it also requires more skill to facilitate students, because otherwise, if we fail to facilitate them well, then it can easily fail, because we need to be able to make the student realize that the responsibility of learning is on them, but we will be there to facilitate and guide them. Now, why use problems? And what kind of problems do we use? Well, if you hear the word problem, what do you think? What comes to your mind? Is it positive or negative? Do you like problems? Well, some people view problems in a negative manner, but if we know how to solve problems, then it shouldn't be a problem. It will be a challenge, but it can be an opportunity. Now, in terms of learning, problems can be multidimensional and integrative. It can integrate a lot of different areas, different fields. It can be a catalyst for inquiry, for learning, and for problem solving, of course. And problems are very good at mimicking the real world demands. And the nice thing is, problems will force us to think back on what we already know, and it activates this prior knowledge and encourages us to learn further about new things that we might need to solve the problem. And really interesting problems can lead to immersion and engagement. And when we say engagement, in a constructivist point of view, engagement means that we take the responsibility for learning and we seek the knowledge. And this is what happens. You know, if we have a problem, think about yourself. Can you forget your problem? No. Well, I think most of us will say that if we have a problem, it's very difficult to forget them. Well, this is because when you have a problem, whether you like it or not, it will stay in your mind. And this is the psychology behind using problems. By posing a problem with elements where the students have to learn in the problem, will cause students to be continuously thinking about the problem. So that's why it's really engaging. Oops. No, I don't know why. Okay. Now, this is the difference between problem-based learning and what we commonly do in class. Now, I'm not saying that what we commonly do in class is wrong, but this is just a comparison. Normally, based on the topic or the outcomes that we have to teach, we are told what to learn, or we teach the students what to learn, the students learn it, and then we give exercises for illustration. So this is the deductive teaching and learning approach. In problem-based learning, we craft the problem and we give the problem to the students, and in the problem there will be things that we would like the students to learn. So the students will have to identify what are those things, and based on the problem, they have to learn the things that they have to, the knowledge that they have to learn first before they can apply it and solve the problem. So this is the inductive approach of teaching and learning, which is actually a natural way for humans to learn. So in a way, because of the problem, the students see that there's a gap in their knowledge, and they have to fill in this gap before they can apply it or solve the problem. And by doing this, we can automatically know whether the students have actually reached deep learning. Now, in problem-based learning, students normally say that it's very troublesome. And it becomes troublesome to them because if they do not reach deep learning, then they will not be able to apply it. But this is where we can see in which part are the students still lacking in understanding. And this is where we really need to facilitate and help them to learn. So it's really powerful for engaging students to learn the new content, and also we can help to develop this self-directed learning skills in students. Now, I have to say here that The purpose of problem-based learning is actually to develop self-directed learners. But as a nice side effect, as a result of problem-based learning, students also learn how to solve problems. And this has been proven so many times. Now, there are three elements in problem-based learning. The first is we should have a realistic problem, and we have the lecturer or the academic staff or the instructor to be designer and the coach. And finally, we have the student as the problem solver. Now, to craft a realistic problem that is suitable for our class, we need to look at the learning outcomes and map the content, attitude, and skills outcome to the problem. Now, as the instructor, a typical instructor will not have facilitation skills. This is where, if we do not have those skills, we have to go for training, because the facilitation skills are very important to help make the students' thinking visible. And we also have to design the proper assessment on both the content and the process. And finally, the students. Well, I don't know about you, but the students that I have do not readily have the skills for PBL. So they should be prepared and motivated, because they are not born problem solvers. None of us are. So this is where we need to help them to develop the skills. Now, when I talk about problem solving, this is a problem solving topology that is derived from the literature, from what is out there on research in problem solving. If you look at what we have as the criteria for problem solving on the left versus what is exercise solving on the right. Now, take a moment to look at them. Which one is more common in the classrooms? Is it problem solving or exercise solving? Now, I don't know about your university, but in most universities here, we find that exercise solving is always very common, because it's really much easier to teach, and it's much easier if you would give them in terms of assessments, it's much easier to grade. Unfortunately, in the real world, it's the problem solving skill that's needed. And research has shown that there's always a problem with transfer, because although students may have learned certain content using exercise solving, research has shown that it's not readily transferable to problem solving. And this is where industry always complain about students, new graduates, not being able to apply what they have learned, although they have passed or they may have done well in certain courses or in certain content. So whether we like it or not, if we want our students to be able to solve problems, real world ones, then we have to give them these kinds of activities in our classrooms. This is a sample problem that I use in my process control and dynamics course. It's a third year chemical engineering course. And by the way, we also use this type of problems for first year students, but of course the technical content is much simpler. So this is the first problem where students have to learn the control structure. They have to learn about how to read a PNID diagram, and among other things. So we give them a setting where they have to go for an interview, and they have to identify the control structures, because they are seeking for an internship at the company. Now, this is actually a fictitious company. It's not a real company, but we make it seem like as if it's a real one. Okay, now, so we have come up actually with a paper on a framework of how to design problems for problem-based learning. So the problems may be real, it's an actual industrial problem, or it's an actual real world problem. It can be authentic. Now, authentic problems are problems that can happen in the real world, but we put it in a different setting so that you don't really need something real for it, but it can be any problem that can really happen, or it can be fictional. So and of course we have to determine the objectives and also the framework of the principles of what we want the problems to be and what we want it to do. Now, going back to the critical the important elements of problem-based learning, we are going to focus now on how to support students as a problem solver, because this is actually very important. Now, in supporting students, we use this concept of scaffolding. Now, scaffolding is actually very powerful because you can use it to systematically support all the students in the class at the same time. So if, let's say, you have 50 students in the classroom, it's possible to support all of them. And personally, I have used scaffolding to support up to 100 students in a classroom, although it is a lot of work. Now, Vygotsky says that, if you have to support the students over the zone of the proximal development. So this is the distance between, if you leave the students on their own at the individual level, so they will just progress on their own. Maybe they will be able to reach higher, but it will take a longer time. But if we assist them with certain kinds of activities or with facilitation, then they will be able to reach higher faster compared to if they were to be left on their own. Now, it has to be over the zone of proximal development, because if the students cannot reach it, then the scaffolding will be too high for them. Now, let's take an example. Can you see the red door on the left here? Now, what do you find strange about this? There's no steps, right? So if you are asked to go up to the red door, can you reach it? So this is the same concept with scaffolding. You need to have the scaffolding over the zone of proximal development so that the students can climb it on their own. So we provide the support structure, but they do it on their own. Now, in problem-based learning, if you look at the typical medical school model of problem-based learning, there's normally 3 phases, where in phase 1, the students get to know the problem, internalize it, and think about what is it that they already know, what they have to find out, and what are the things that they have to learn first before they can solve the problem. So this is about meeting the problem and problem identification and analysis. Next, in phase 2, they learn together, they teach each other, they synthesize the knowledge, and they apply it to solve the problem. And then in phase 3, they present what they have done, how they solve the problem, and they reflect over their learning process. And finally, the closure must be done by the facilitator. Now, the thing is, the typical medical school implementation is in a small group where there's a maximum of 10 students with 1 facilitator. Of course, when I wanted to apply this, I couldn't use it because in my classroom, there's at least 50 to 60 students at that time. So since I was already implementing cooperative learning at that time, and the purpose of cooperative learning is actually to form learning groups so that the students can work together as a team to learn together. But in cooperative learning, if we want to make it work, there has to be these 5 principles embedded. So what we did was that, looking at the pattern of cooperative learning, where there's individual construction, interaction with the team member, and an overall class interaction with the instructor, we embedded this pattern into the problem-based learning cycle. So then we came up with this. So the 3 phases are still there, phase 1, phase 2, phase 3, except now it has been expanded because we have embedded the cooperative learning pattern into the cycle. So now there's individual meet the problem, then there's team discussion, and then there's an overall class problem identification and analysis. In terms of peer teaching, they have to prepare individual notes, then there's peer teaching in the team, and then there's an overall class discussion. So it goes on until the end for phase 3. So I want to show you a video. Now the audio doesn't come out, but it's just background music. But I'm going to explain through what happened in the classroom through this video. Okay, this is where we embed the principle of cooperative learning into problem-based learning. These are the principles that we use to design a CPBL learning environment. So this is the framework that students go through in the classroom when they learn using CPBL. Oops. Sorry. I don't know what happened. Okay. Okay, so this is during the presentation and the closure. So this is part of the classroom activities during peer teaching. By the way, these are just examples and it can be done in several ways. Okay, I don't know why it's frozen like this. Just now it was okay.
The bandwidth issue, don't worry.
Yeah, I don't know what happened, but
It might be just the bandwidth. Yeah, that's fine.
Okay. Could be the bandwidth? Yes, I think so. So anyway, you can see that we do use real industrial problems, but don't give it as a problem to the students. We give it in series, then only then do we, at the last part, do we give a real industrial problem to them. Okay, this is the final presentation. In this case, this is the final problem presentation, and it can be done in several ways. Okay, we'll stop there. That's okay. Well, I hope you can see some of that.
Yeah, that was really good. That was really good. I think it worked out well. Yeah.
Okay. Yeah. Okay. So, oh, sorry. Okay. So now, the thing is, when you want to do problem-based learning, it's not that like you have to have a problem for the whole semester. It can be small problems. Like I've done small problems over 1 week for a 3-credit-hour course. That means I have 3 hours in a week. So I've done it over 1 week. I've also done it over a maximum of 3 to 4 weeks for a problem. So it depends on how big the problem is. And as we got better, we began to have a series of problems that is where the story is actually interconnected to one another, but those are actually separate problems. For our first year course, we designed one whole big problem, but we divided it into 3 or 4 parts. So it's up to you how do you want to do it. There's several ways that are possible. Now, for example, for our control course, this is what we did. We have 4 problems, and the first problem we made out the story that they are going to be interns. So they are still in the university, but they are applying for internship. In the second part, they have just graduated. So now they are engineers. And in the third problem, now they have joined the technical services department, and they have to look, they have to do more. And in the final part, we pose the problem as now they are working in a consultant firm. They have to design a control, propose a new control system for a plant. So if you look at this, this is the sample problems for one semester. Okay, so this is like they are going to be the intern. This is when now they have that they're now an engineer. And when in this part they have to tune controllers, and so we begin to put in even simulations, softwares for them to use, like for simulating how to do the tuning. We post certain things that say, well, they have to use Simulink or MATLAB or MathCAD to look at the dynamic behavior and do the tuning. So this is for the last part. They have to design an automatic control system. In this case, CCM Chemicals is a real plant that is not that far from our university. So we got permission for them to bring the students there. So you can scaffold in this problem some, if you want to use certain softwares, if they did certain skills, if you want them to go to the lab, it's up to you to integrate it into the problem. And now the beauty of using the problem is that it's not limited to one course. It can also be used in a systematic manner throughout some courses. So let's say if you have two courses where the instructors agree to use problem-based learning, so you can actually combine problem and have one big problem for the two courses where the different courses will take care of the different parts of the content. Okay, so this is the nice thing about it. So then it's just one problem for two courses. Because if you have one small problem for each of the course in the same semester, it will be too burdensome for the students. Now, when we talk about scaffolding, it's not only for the skills, it's also for motivation. And research has shown that you need to support the students, because if it's the first time where they have to face real world problems, it can be very, very challenging for them. So researchers, psychologists say that and whenever there's a big change that we as human beings, normal human beings, have to go through, then there's a trauma cycle that they need to overcome before they get to a positive part. So when they are facing shock, denial, strong emotion, this is where you need to really scaffold them, to explain, to motivate, and to rationalize. And we found that most of the time, if you know this, if the instructor knows this is happening, then it's quite effective that if we can support them, then they will just go through and come up from here better. So this is an example where we track some students throughout the semester. If you see in this journal on the problem solving skills, you can see that the student is really not that happy in the first part. It's a big pressure for me to handle. We have to face the first stage, that's completing the report and presentation, so it's really burden. In the second reflection journal, which is in the middle of the semester, this student said that, well, we have to do a lot of research, it's very stressful, there's a lot of tasks to be completed. So this is, you can see there is acceptance here, although still not very happy. But if you look at the last one, the student declared, honestly, I'm happy. And it's not easy, like they need to brainstorm like a half-dead person, but then it taught the student to be patient and to go through it until the end. So, when you do problem-based learning, don't give up. When the moment you see negative feelings among the students, understand this. And I actually show the trauma cycle to my student. And from our research, we have actually found that CPBL effectively enhance students' motivation and learning strategies, problem-solving abilities, and team working skills significantly. Now, this is one focus group discussion report. one of our colleague, Johannes Strobel from Purdue University, came and did a focus group focus group discussion with some of the students who had undergone PBL. This is on industry experience, PBL between an industry experience. Oops. The students said that, well, they're not afraid or unprepared for their industry experience since they counted PBL as a small industry experience. And they say that there's actually similar task between the problem that we have given them and what they see in industry. Of course, in industry, it's a bigger experience, it's a larger experience. They're required to do more. Now, I always get this question, so I put in this slide. What is the difference between problem-based and project-based? Well, actually, for me, if you're doing problem-based or project-based, it doesn't matter if you're able to use real-world problem, because because the students will learn a lot the moment you start using real-world problems. But this is just if you're writing about it and if you're really particular about terms. Problem-based learning is more of to help students acquire knowledge, to be self-directed learners. The learning is more inductive. But problem-based learning is about integrating knowledge. It's the application of knowledge from what the students have learned. And in problem-based learning, you have to define what the students have to learn. In project-based learning, you're not required to, because it really depends on the students sometimes to dictate what they want to have in their project. Problem-based learning always must start with a problem. Project-based learning, it depends. Process-based in problem-based learning, task-based, and product-based in project-based. Problem-based learning has very systematic facilitation. There's a variety of approaches for project-based learning. It depends on what you want to do. The all-board model uses a lot of supervision and project management. Then in problem-based learning, there must be a closure and a process reflection. In project-based learning, well, the all-board model has reflection, has a process analysis. In some, yes, some no. So it depends. So does it really matter if it's problem-based learning or project-based learning, if real-world problems are used? It depends on what you want to get in your class. What is more important is what happens during the learning experience. And so let's not argue over that. If you're able to do any of them, it's fine. And I've used both. And for your information, the CPBL framework also works for projects. Because when I do projects, I also use Cooperative Problem Based Learning framework as a scaffolding for students. So if you look at the 21st century skills, all three of them, when we train instructors and also teachers to use the CPBL framework, they could see that they're able to actually tackle all the three skills. Now, unfortunately, if you're not used to implementing active learning or team-based learning, it can be quite challenging to jump straight to PBL. So our advice is to go and do it gradually. Do active learning first, and then do something on team-based learning, and then you start to add in problem. I've seen a lot of people giving up when they try to use problem-based learning without really having any initial experience in doing active learning or team-based learning. It's not that it's impossible, but there has to be certain skills before we are able to make that jump. So even in my own experience, it helps to have the simpler, smaller scale activities, because the active learning and the team-based learning activities are those that you can actually use for scaffolding when you use problem-based learning. So I think that's about it. That's 30 minutes. I promise, Krishna, I'm going to talk for 30 minutes.
Okay. Wow,
Thank you very much.
Fantastic. I'm sure there's a lot of questions that has been generated. I think I can think of right off the bat, actually, the clarification between the difference between problem-based learning and project-based learning. Most people really have an issue with that, and I'm sure even after listening to you, I think people might be scratching their heads what is the difference between the two, and that's fine. But that's the whole process of learning, right? When we try to discuss these things, and everybody has slightly different approaches to think about these. Fantastic. So we have plenty of time for some interaction, and obviously I've selected a few people from the audience. We have almost 100 people here with us. Select people in the audience and put them on the panel, and I will touch on them to make a few comments, brief comments, when after a while and in a little bit. But in the meantime, I want to pay more attention to the people in the audience itself and see if there are any comments and questions from the audience, and I'll read out some of the comments that have come, and then maybe we can start with those and then move on to some other people on the panel list that I've created. So obviously one good question. Unfortunately, I think she has left. Maybe she has a meeting, but LC Mao has said, are these excellent slides, will they be available after the webinar? So if you can email me some of these slides, Khairia, I will send them out to IFE's office, and they will make them available as needed. So that's good.
Yeah, sure.
And then of course the issue of deductive and inductive classroom learning, you laid it out quite well. But I think it's something that needs to be reinforced again and again, and maybe you can go back to that slide on the difference between the inductive and deductive classroom. Can you just spend 30 seconds to maybe re-emphasizing that that's a very important concept and at the root of the whole thing?
Yes, it is very important. Well, we normally teach using deductive approach. It's based on the class syllabus and the outcomes. We design the learning environment. We explain to the students that do certain things to learn, and then we give them examples and we give them exercises after that to reinforce it, right? So that is deductive. You start from the theory and then you go on to the examples. The inductive approach is if you give them problems or examples or of where it's happening in the real world, and then the students will actually identify what is it that they do not know in the problems or in the examples or in what is happening. And then they will start to form questions and then identify what's the gap in their knowledge. They go and find out. So this is where they learn. And then they apply it. They try to explain what you have given them or solve the problem. So it's the other way around. You start with the problems. You start with the examples first. You start with the real world phenomena first before you actually give the theory. So does it make sense?
Yeah, it makes sense, absolutely. And it's another question from the same person, Prasad. I think the key to all of this, Khairia, is obviously training of the faculty, because 99.99% of our faculty are used to doing it the other way. So how do we? What has been your experience in getting novice faculty members to slowly start learning how to do this? What kinds of things are most effective in terms of training them?
Okay, now I normally get them to think, you're teaching something, where is it used? Why is it important? So what is, because one very powerful aspect of learning and a very important motivating factor is how would the students use it? Why is it important for them to understand it? So start from there. Start from real world examples of where those theories are being used. And then you will start to poke the curiosity of the students. Then they will need to find out, okay, why does this happen this way? So that's about it. Good. Think about where it's being used, how it's being used, why it's important.
And the point you made about scaffolding, skills in scaffolding, I guess one can start with simple things like active learning and team-based learning, and slowly build up to the more sophisticated dimensions of problem-based learning. A question from Khadim is, can you find the video that you showed on YouTube or somewhere? Maybe there's some, maybe you can send something to me. Okay, so if it's later on. And this LC who has left us has a question, what works best for you in building real-world business context into your problem-solving approach? How could the business community contribute more effectively to your approach? That's a good question, very good, relevant question.
Very good. Because when I showed the video where we have the real industrial problems, That is the most difficult to get. Usually I will start before the semester to get to try and get a company that will allow us to bring the students in and to help us with the problem. And usually I will approach at least 10 companies, because then I'll end up with one. At least one.
Yeah.
Usually out of 10 I'll get one.
Excellent.
So you know, if the if
well,
the
Elsie,
yeah.
cheers. It's okay. Elsie is there. I'll ask her to speak for herself. Elsie, as I thought you lost connection, I thought, but let's see. And get her to say just hello. Elsie, come in. I was being proxy for you. Come in, Elsie. You can unmute yourself, Elsie, but while she's doing that, question is, I think a lot of times people, faculty and students, they think problem is a numerical thing, but I guess you have this here, in this context, problem is a very vague situation out there, right? I mean, that's a lot of students will say, oh, give me a problem. It's a numerical problem. I'll plug in my computer and get a calculator, get you the answer for the problem, right? That context of what's the meaning of word problem. What is any comments from you on that? And then Elsie is back. So go ahead, Khairia.
Okay, a problem, most of the time when you look at the problem, you don't really know what's the problem. So you need to identify the problem first. So it's not really clear. And we make the students go through phase 1, where they need to restate the problem in their own words. What do they understand about the problem? And this is very important because they're working in a team. And if each person do not state what they understand about the problem, they will be trying to solve a different problem altogether, each of them. So this is about the problem identification stage, because in the real world problem, not everything is clear cut.
That itself is a major part of the problem of problem-based learning, is identifying the problem.
Yes.
So that was a question from Yagneshwaran. Elsie, you want to jump in there?
Oh, yes. Thank you so much. Can you hear me now?
Yeah.
Yes,
okay,
yes.
Thanks so much. This is a marvelous presentation. And, I'm particularly interested from the business side with the issue that you started with, which is, business complains, if you will, that they have a lot of training to do of engineering graduates to actually become productive once they're employed. And you have put your finger on a way, an inflection point in how to address that. But it occurs to me that business needs to cooperate by the same token so that you can actually make that bridge. And I'm wondering, are there mechanisms, are there formal mechanisms and processes so that you can more easily construct those problems that are relevant to them? Is the problem that you have to initiate the contact and only 1 out of 10 agree to collaborate? Is there not a mechanism, or is that something we should work on?
Actually, from the center that I'm heading, we are setting up a problem shop or a place where companies can give the problems, so that then we can write the problem again to make it suitable to bring into the classroom. So if there's companies who want to contribute problems, we will be more than happy to receive them. And we will see where those problems are suitable and let other faculty members know that there's problems available for them to use.
I love that concept, problem shop.
Yes. So anybody can shop for the faculty member anyway can shop for the problems, and we can help if you're willing to also come in as an external expert, as a scaffolding for the student. Then we can do that.
Okay, great. Thank you.
Question about time management from a couple of people, both in the classroom as well as in terms of the students managing their time with respect to other courses that they're taking. Comments on that?
Okay. Now, this is what I found. And when I first started using problem-based learning, I asked my students, what have I deprived you of? And they say that now we cannot go window shopping. Now we cannot watch Korean movies. Now we have to delay our gaming. So I didn't really feel that guilty when I started using problems, because for other courses, yes, they have other courses, and some did say that, everything went haywire, but that was during the first problem. Then we guided them on how to manage their time. And after that, in fact, they say one of the skills that they got was time management. So we made sure that they know how to arrange their time for their meetings, to actually have an objective for the meetings, and not to have very long, unproductive discussions.
And in the classroom itself, how do you find the time management, faculty managing the time?
Well, you see the CPBL cycle.
Mm-hmm.
So if you're at the start of the cycle, normally you will need an hour for the problem identification, for the whole class problem identification. For the peer teaching, you will need a 2-hour class. And for the presentation, usually a 2-hour class. So you can actually plan how your class go. So we have just added, like for the control class, it's a 3 credit hour, but we have 1 hour tutorial. So we have 2 hours, 2 hours, twice in a week. So we arrange it according to how our class go.
Good. A couple of questions here about the class size. You mentioned that you have done it for 100 students, and that's interesting. That it's a lot of work, obviously. Any quick comments on the dealing with large classes?
Okay, I don't advise large classes. When we did it for 100 students, I had help from other lecturers. But then after that, because we saw that this is working, we started limiting the number of students in the class because we want this to be done well. So like in the first year course that I'm teaching where we use problem-based learning, now it's limited to 40 students. Mm-hmm. So if you have a large class, you need to train your graduate students or get other faculty members to help.
Okay, does this include courses from the first year onwards, or is it just limited to the final year students?
No, first year. You
start from first year, all the way from first year to fourth year throughout.
Yes.
Okay, great. How about assessment of the students in this kind of an approach? How would you grade, assess the students in this environment that you are proposing? Individual assessment.
Now, it depends on what you want to assess, but I use the principle of constructive alignment. So in constructive alignment, what is your intended learning outcomes? What is the teaching and learning activities? And what's the assessment tasks? So in the, for example, in the problem identification stage, there's an individual part. So I ask each student to submit their problem identification individually, just to make sure that they've done it. Mm-hmm. And then they discuss with the team, and then we have an overall class discussion. So they do submit individually for that part. Mm-hmm. The individual peer teaching notes, I ask them to submit also, so that then they would have something to bring to the team. And great. After that, they'll have an overall class discussion.
Let me quickly jump to couple of folks in the panel. That Ramiro, you wanna jump in and make a few comments here, and then John Tharakan. I noticed some of the others have snuck away. Ala is there. After that, Ala. So Ramiro, any comments to add to the discussion? Yeah.
Thank you, Khadija, for a wonderful presentation. This just hit it on the nail. This is something that we've been discussing with companies. They addressed that this problem-based education they needed because of employability. They're not finding the right engineers. So what you're doing is just great. It's something that we have been following too here at UNM. And a recommendation that we started at UNM is we had our shop, like you mentioned. This is for all undergraduate students that we want to bring quickly into research. But I think this can be expanded to industry. And I agree with you, it's very difficult to get industry engaged. So this is done through the advisory boards that we have in each engineering department and at the dean's level. Those advisory boards can be used to bring some really challenging problems into the classroom. But I want to congratulate you on a wonderful presentation. Thank you so much.
Thank you, Ramiro.
Thank you, Ramiro.
Yeah, just by the way, all the previous questions that I asked before were actually from the audience. A lot of people had sent in questions, and I was trying to combine and summarize a few of them which had common themes. So appreciate all the excellent questions that came, and keep continuing sending your comments. I might have a few minutes at the end. John Tharakan, would you like to jump in, and then Ala after that? Any comments from you, John?
Good morning. Thank you so much for that presentation, Carrie. That was wonderful. I echo the comments. I think this is wonderful work and needs to be dispersed across engineering curricula and programs. One of the comments that I have and one of the concerns I have is the selection of the problem. And one of the things that I have done in my intro classes is actually getting students to identify a problem, and through either newspapers, journal articles, whatever, so that they actually have a part in the selection of the problem and sort of buy into the whole process in a better way because of that. So I wonder if that's something that you might also consider incorporating, and not just focusing on industry problems, but also on community problems, and thereby facilitating perhaps engagement of students in service learning type of activities combined with these problem-based learning. So that's I really appreciate your presentation.
Okay, what I was showing you is the one for the third year course. In the first year course, I'm actually teaching the Introduction to Engineering course. We have a sustainable development theme problem.
Okay.
So what we do is is divided into 3 parts. The first part is about students learning about what is sustainable development and what is happening in the world compared to what is being done in Malaysia. And what is being done around them. So then that's the first part. That's the learning outcome for the first part. The second part, we ask them to collect data, because we want them to see, let's say for, I'm giving you an example, let's say for water conservation. So we ask them to actually audit themselves, how much water they're using and how much water are their friends using, how much water is being used in the colleges. And since they are first year students, they have to learn about flow rate. They have to actually measure how much water is coming out of the tap, out of the shower, how much water is being used when they flush, and if there's any water leakages around. And this is actually the precursor for them to identify a problem for the third part. Because in the third part, based on the data that they have collected, they have to identify a problem and provide an engineering solution for that problem. Of course, we do not ask them to build it, or even because we don't have even the budget for the prototype, but they do it until the design stage. So this is a proposal, this is a design, and how much it's going to cost. So we do ask them to look for problems themselves, but that is not the first part. That is the third part, because in the initial part we are actually scaffolding them to have better skills at identifying the problem, have better skills at collecting data and making decisions on what is actually to zero in on what is most important for them, that the problem that they want to solve.
Okay, great. Give Allah a couple of seconds, a minute here. Allah, come in. Allah, you want to say something?
Yeah, thanks for a wonderful presentation. I would appreciate if you can elaborate a little bit on the concept of scaffolding. How if you can give a couple of examples. Is that something that's done by people from the industry? Is it just support that the students give to each other? Is it something that you do? If you can just give a couple of examples.
Okay, Allah, what you said is all of them.
I knew that.
Yes, you knew it. So the scaffolding can come from the instructor. The scaffolding can come from their peers. The scaffolding can come from an industry expert. The scaffolding can also come from a lab technician. So it's whoever you have assigned to support certain aspects of their learning, or to motivate, even if to motivate them. So you can also get those industrial people to motivate them. And I have even asked the help of the students who have graduated to come back and talk about problem-based learning, so that the students will be motivated to go through it.
Yeah.
So one example of scaffolding that I give to my students, because I want them, for example, let's say I want them to use Simulink for simulating the control system, the controllers. So instead of asking them to just explore on their own, which would take a long time, so I can ask one of the graduate students, or I can do it myself, to have a 1 or 2 hour workshop on getting started with Simulink and how to plot and how to input data and so on. So that is also a scaffolding.
There are a lot of online resources also, some YouTube videos. I found that to be very useful when it comes to software, getting started on software nowadays. There's plenty of stuff on the internet.
Even MATLAB and Simulink has tutorials that you can just give to students. So if you have a YouTube video that can actually provide help your students in some of the knowledge that they're required, you can give them the link. That is also a scaffolding.
Okay, thank you, Ala. Just to close, I have a couple of commercials I just want to put up here. One is actually the WEAF 2019 coming up in in November 13th to 16th in Chennai. Invite all of you to go to the website, and abstracts are due on June 30th. And fascinating, exciting thing. And we plan to have a side trip after WEAF to go to Delhi, Agra, see the Taj Mahal, etc. So keep lookout for all of those things. And submit papers, come to WEAF. And another important big announcement is the award, the Duncan Fraser Award, that I think we need nominations for that. And in fact, Khairia herself is the recipient of this award last year. This is the IFES Duncan Fraser Gober Award for Excellence in Engineering Education. Recognize individuals who made innovative, meritorious contributions, significant impact on advancement in engineering education. So now you can see the caliber of people that we're looking for to be nominated for this award. This is the one that made the presentation today. So the process will be to download and complete nomination from the IFES website. To review the nomination, all nominations will be supported by an IFES representative. The prize includes economy round trip fare to Chennai, where receive and $1,000, and so that's the that's the commercial that I was asked to by Hans Hoyer, who was here most of the time but had to leave for another meeting. So please come to this WEAF, which is the concept is disruptions in engineering education. And in fact, what we talked about all this whole hour is in fact a disruption from the conventional way of teaching. So these are the types of things that we want to hear from all of you that you've been trying. Deadline June 30th for the abstracts, and please come, all of you. Okay, so thank you very much, everybody. We have come to the end of our session here. And any last words, Khairia, from you before we sign off?
Well, I think I hope all of you have gained something from the presentation, and I will be sending the slides, and if there's any questions, I'll be happy to just send me an email, and I'll try my best to answer them.
Yeah, many people have sent comments saying excellent presentation, and they also have other comments which I will follow up later on with them by email. Thank you very much, Khairia.
Okay, thank you. Okay, bye.